So today we are going to cover basic electrical quantities. So let's talk about charge first. Charge, specifically electrical charge, is the property of a particle or material that enables interaction with an electromagnetic field. Now, I'm fully aware that most of you probably have not yet taken Physics 202, and so you very likely don't know what the heck it is I'm talking about when I refer to things like electric fields and magnetic fields and electromagnetic fields and all that kind of good stuff. That's perfectly okay. We are going to use those terminologies very, very briefly in this class. We're going to bring it way back down in scope to more circuits related stuff here. But effectively, all of that sentence means is that because matter contains protons and electrons, we can use it in circuits. That's it. Anything that contains electrons and protons can be used to conduct electricity, which means we can get a voltage across it, pass a current through it, apply power, all that kind of good stuff. So nothing particularly fancy there, all right? Charge is a quantized property. The fundamental charge, Q, lowercase q, is equal to 1.60218 times 10 to the negative 19 coulombs. So capital C there, the unit of charge, is the coulomb. A proton has a charge QP is exactly equal to Q, our elementary charge, and an electron has a charge Q sub n that is equal to negative Q. We can't subdivide this charge at all, okay? So because there are going to be integer multiples of electrons and protons in matter, any charge that we ever observe will be an integer multiple of that 1.60218 times 10 to the negative 19c. Now, because that number is so darn tiny, 10 to the negative 19 coulombs, charge appears to occur over a continuous scale because the division between different levels of charge is so small that it's hard to observe, okay? So charge is a quantized property, but we're not going to go through the pain of, counting things and making sure that we're at exactly an integer multiple of that because the number is so small, it'll all work out in the wash, okay? Charge is also a conservative property. And so that means that it cannot be created or destroyed. The amount of charge in any system is fixed. So we can't get more charge out of a system than we put in. And that's going to be very, very important for us to understand concepts like Kirchhoff's current law and how current flows through a capacitor and things like that, okay? The next topic that I want to talk about, we really have a choice here. We can either talk about voltage or current, and they're related. So which one I talk about first kind of informs how I'm going to talk about the second one. So which one do you guys want to talk about first, voltage or current? Current, okay. So current is the time rate of change of charge flow along a path. Or an alternative definition. Whoever that was, please mute yourself so we don't have all kinds of weird feedback. The amount of charge that passes a point in a circuit per unit time. These two things really mean the same thing. It's just two very slightly different ways of looking at stuff. Okay. So mathematically, current, which has a symbol I, is simply the derivative of charge with respect to time. And so what that means is that if the amount of charge passing a point in a circuit stays constant, we don't really observe a current. We need to see a change in the amount of charge in order for current to flow. Before we move along, we can take this relationship here and rearrange it slightly, right? So this equation tells us how to calculate current given a particular charge distribution or mathematical model of how the charge is behaving. So we can rearrange this guy and find that charge Q of t is the integral of current. Sorry, this should not be T naught. I'm not going to use T right here. I want to talk about what I'm about to do, okay? So the limits of this integration are going to include time. And we're also talking about a function that changes with time. So I'm going to do, I'm going to put in what's called a dummy variable. Sometimes I use T prime, but I stopped doing that when so many students thought that meant to take the derivative with respect to time, which is not exactly what we're doing at all. Some textbooks use the Greek letter tau as a dummy variable for time, but I don't like to do that because we are going to use the Greek letter tau to represent time constants in RL and RC circuits in about 3 weeks. So I'm going to use X. X is just going to be a dummy variable representing time. Okay, so in your head, treat it just like it was T, but I'm just trying to make sure that my equations are mathematically correct. All right. So I of X, where X is a dummy variable for time, dx, the limits of integration here are from T naught, and I'll explain what that means, to T, which is just some point in time that we are interested in. And then added to this integral, I will have Q at T naught, okay? So let me scribble some stuff on this guy. X is a dummy variable for time T. So I'm using x purely because t shouldn't show up in the equation that I'm taking the integral of if it's one of the limits of integration. Yes, ma'am. That's a fantastic question. It is not in the integral because it occurs after the dx. The dx bit is what is the last part of our integral. So the q of t naught is absolutely not. So what we're saying here is that charge is equal to the integral of current plus some amount of charge that we know at time t naught. So t naught is what we would call an initial condition on our system because we know something about how the system was behaving at a particular point in time. So that's the next thing I'm going to write down here, right? T naught is, and that doesn't look. So T naught is a point in time at which we have a known value. And here, I'm going to put this part is not inside the integral. I'm very glad you asked about that because it's a very, very common mistake. So easy to nip it in the bud now because somebody brought it up. Okay. So before we move along here, I know this equation looks a bit messy, but let's put it into practice so that we can understand exactly what the hell it is that I'm talking about. Okay. So let's say that I have the following graph. I like to give questions on exams and all that kind of stuff that makes you guys be able to read a graph. So fair warning. So let's say that our horizontal axis represents time in seconds, and our vertical axis represents current measured in milliamperes, which I guess technically I haven't defined the unit of current yet. So I'm going to do that right up here. The unit of current is the ampere, which is fundamentally 1 coulomb per second. The unit of charge is the coulomb. Right? And let's say that our current waveform looks something like this. It's 0 for a long time until t is equal to 0, at which point our waveform kind of turns on. And then it decays. Let's say that this time right here is 10 seconds. This time right here is 20 seconds. And our current has a value of 10 milliamps and then decays down to 0. All right, so what we could do is develop a piecewise expression for the current flowing through our element of interest here. Oh, and one last thing, I want to say that Q at t is equal to 0 is equal to negative 25 millicoulombs. So this will give us some initial condition that we need to account for. Okay. So we could break this function up into multiple parts, right? What I mean by that is we could say that I of t is equal to 0 amps for t less than 0 seconds. It's equal to 10 amps for 0 seconds is less than t is less than 10 seconds. And then I can use the simple y is equal to mx plus b format here and figure out what the charge behaves like over the interval from 10 to 20 seconds. So I can see right off the bat that it decreases 10 milliamps in 10 seconds. So that would be negative 10 milliamps per second, which is my slope, times t minus 10 seconds for t greater than equal 10 seconds. And then it's 0 amps again for t greater than 10 seconds less than t less than. The thing that probably some of you are scratching your head about is where the hell did that t minus 10 seconds bit come from? That's pretty fair. Hopefully you guys in your pre-calculus class learned about time shifting functions. And so effectively, I'm treating that as if it t is equal to 10 seconds is my origin. Oh, and then actually, I have a y-intercept. Sorry, I've made a mistake here. Let me fix that. I have a y-intercept at t is equal to 10 seconds of 10 milliamps. And then the limits on that guy should still be 10 seconds less than t less than 20 seconds. Anyway, I can apply the time shifting theorem and I get this guy, and this is my piecewise function. Then I would have to throw all 4 portions of that piecewise function into my integral and do a bunch of stuff, okay? I don't like making you guys do that amount of math. So this is mathematically correct and mathematically rigorous, but let's think about what the hell it is that we're actually doing here. What are we doing? The area under the curve, which is a square and a triangle. So instead of thinking about how to form a piecewise function and all that crap and then doing all of the actual calculus, let's do it the easy way and just take the area of that square and the area of that triangle and apply the principles correctly, and we'll get the exact same answer, but using a lot less math, okay? On your exams and homeworks and all that kind of stuff, this is the type of calculus that you're expected to do for the most part. If it's not a simple sinusoidal function or an exponential function, it is going to be, you're looking for the area under the curve of something that you can break into rectangles and triangles, okay? So you don't have to remember all kinds of weird integrals and derivatives and all that kind of good stuff, or how to set up piecewise functions and all that kind of stuff. For the most part, it's going to be this straightforward. All right, so our current, excuse me, the charge at any time greater than t is equal to 20 seconds is simply going to be this guy here, area 1, plus this guy here, area 2, plus q at 0. Just because I'm doing the calculus in an easy way, or I'm taking the area under the curve to be the area of squares and triangles, doesn't mean that I can forget to include my initial conditions, because that absolutely influences the amount of charge overall in the system. Okay? So in this case, what should area 1 be? Yes. No, that's a good question. So I'm doing t greater than 20 seconds because I'm accounting for all of the charge that's being accumulated while this current is on. So if I did it at a time less than t is equal to 20 seconds, we would, the amount of charge would still be changing, because the current hasn't settled back down to 0. Does that make sense? Okay. So what's my area A1 going to be? Units are very important here, okay? So I have a rectangle. What's the area of a rectangle? Base times height, right? So we have a base of 10 seconds and a height of 10 milliamps. And then I have my right triangle, A2. What's the equation for the area of a right triangle? I'm asking you guys this because I think it was the summer of 2018. I had 21 students enrolled in my summer circuits class. 5 of those 21 students could not, for the life of them, remember what the equation for the area of a right triangle. So that's why I'm harping on it right now. If you don't know what it is, please sit quietly. You're about to learn. Somebody who remembers their 3rd grade trig or whatever, shapes and all that jazz, tell me what's up. 1/2 base times height. So 1/2, the base here is still going to be 10 seconds. The height here is going to be 10 milliamps. And then Q at t is equal to 0 is negative 25 millicoulombs. So I'm going to add negative 25 millicoulombs. So when I multiply 10 seconds times 10 milliamps, what does that give me? 100 millicoulombs. Absolutely right. And then 1/2 10 seconds times 10 milliamps is obviously 50 millicoulombs. And then I have my negative 25 millicoulombs. And so the total amount of charge that enters the element in the interval 0 is less than t is less than 20 seconds is exactly 125 millicoulombs of charge. All right. If you wanted to suffer through throwing those 4, creating 4 different integrals and adding up all the results and all that kind of crap, by all means, do it. You'll find out that you get literally the exact same answer we got adding up rectangles and triangles. Okay, so this is, for the most part, the level of calculus I expect out of you with regards to functions that are not simple exponentials and simple sinusoids. Okay, so let's circle back around to the concept of current here, all right? In your Engineering 120 series, all of the circuits that you dealt with contained only voltage sources, batteries, right? In this class, we are going to deal with circuits that contain current sources, DC current sources, AC current sources, and all that kind of good stuff. So we need to make sure that we're very clear about how we represent currents in a circuit, okay? So if I have a generic circuit element, let's just call it element A, I can say that a current passing through it, I would identify it like this. I'm going to have an arrow that indicates the direction of current flow. And then I'm going to have some text that is the magnitude of current that's flowing in that particular direction. So in this case, if we said that 5 amps was flowing down through element IA, what would be the current flowing up through element IA? Negative 5 amps, exactly right. So if it's in the opposite direction, it has the opposite sign. So if you're ever working on a problem or anything like that, and you're given negative currents, and you don't want to carry around that extra negative sign, you can throw away the negative sign by simply switching the direction of the current, okay? So currents are defined. That is not how you spell defined. By a magnitude and direction. You need both of those things to fully identify a current. Okay. So saying that there's a current of 5 amps flowing through a resistor means nothing unless you tell me what direction the current is flowing through as well. Okay. You need both of those pieces of information to fully identify a current. We represent current with an arrow indicating direction and a magnitude. Okay, so that's how we talk about the current that's flowing through a particular element. Now let's talk about the various different types of current sources that we're going to utilize in this class. So the first current source that we're going to talk about is this guy. So it's a 2-terminal device. It has an arrow, and then it will also have a label. So that label IS is telling us how much that current source supplies. And that direction tells us, or that arrow tells us the direction in which the current is flowing. Okay. So this guy is a DC current source. And it is an example of an independent source. Later on, we're going to see something like this. This guy is an AC current source. And it is also an example of an independent source. So it has effectively the exact same symbol, except that there's a little squiggle on the arrow that tells us that the current varies in time. That's why our magnitude also varies in time. So IS of t is an AC or alternating current source. Okay. So let's talk about what I mean by independent now that we've covered 2 different independent sources. Okay. An independent source means, or specifically an independent current source means that the current passing through the element does not depend on an outside quantity. Meaning that, let's say that IS on the left-hand current source were equal to 5 amps. That current source would supply 5 amps of current regardless of what it is connected to. Okay. The voltage drop over that current source, we haven't talked about voltage yet, but the voltage drop over that current source will be whatever it needs to be to make 5 amps flow through that current source. Okay. So the 5 amps or the IS is a fixed quantity. And then the voltage drop across it is whatever it needs to be to make things work. Is that clear? All right. So we have 2 other types of current sources here that we need to bring up. And for the first couple of weeks of class, you guys are going to hate these. Some of you will hate them the whole time. That's okay. So this guy is a voltage controlled current source. And then we have our last guy, I'm going to put way over here to the right. This is an example of a current controlled current source. And both of these are what are called dependent sources. All right. So let's talk about these guys fundamentally real quick. All right. Literally, simply by looking at their symbol, we can see that when it's a circle, it's a dependent source. Excuse me, when it's a circle, it's an independent source. And when it's a diamond, it's a dependent source. Okay. I know that that seems trivial, but it's actually kind of important to remember because some of you are going to forget that. All right. Let's look at this guy in the third one from the left here, the voltage controlled current source. Okay. It has some quantity G multiplied by Vx, where V is representing a voltage somewhere else in the circuit. Okay. So the amount of current being supplied by that source depends on a voltage. So that's why it's a voltage controlled current source, okay? So just because there's a Vx there does not mean that this is a voltage source. Anytime we have an arrow, we have a current source, okay? Doesn't matter if that current is controlled by a voltage or controlled by a current. If there's an arrow in the middle of the schematic symbol, it means it's a current source, all right? The guy on the right is a current controlled current source, which means the amount of current flowing through that source depends on a current elsewhere in the circuit. Now, some of you are probably asking yourselves, well, where the hell would we ever see something like this? And practically, and the answer is transistor circuits, which we are not going to deal with in this class at all. But I do need to set my electrical engineering students up with the knowledge to handle it. So that's why the rest of you have to suffer through these things, unfortunately. So these are all current sources. Some of them are independent, others are dependent. Let's talk about that coefficient there, G, okay? So this is a current source, so it outputs current. It's controlled by a voltage. So what do the units of G have to be? So think about it, the input is voltage, the output is current. Exactly right. So G has units of amps per volt. What should the units of K be? The coefficient for the current controlled current source. None or amps per amp, either way works for me. All right. There isn't. So you can tell whether it's a current controlled voltage source or a current controlled current source or a voltage controlled current source by whether or not it's literally controlled by a voltage or a current. Yeah, and so it's buried in the magnitude portion, not the symbol itself. Yeah, but that's fair. This symbolically, they are absolutely identical. It's just whether or not there's a V or an I in the definition of how much current is flowing tells you which one it is. That's a very reasonable question. Any other questions regarding currents, current sources, or anything like that? All right. So let's talk about voltage. We're going to have two word-based definitions, and I'm going to write those in a couple of minutes, but I first want to talk about the mathematical definition because that's where both of those other definitions come from, okay? So mathematically, the voltage, I'm going to call it VAB, is defined as the integral from A to B of the electric field vector E dotted in to a differential line element dl. So a bunch of mathematical garbage that most of you don't have a damn clue what it means, and that's perfectly okay. All right. For those of you who have had Physics 202, do you remember what the relationship between Coulombic force and the electric field is? Anybody have that? All right. Everybody's keeping quiet, and that's okay. So I'll give you the answer. Electric field is related to force on a charged particle as simply F over Q. So the force, electric field is simply force divided by charge. So this is the integral from A to B of Fe, the electrostatic force, divided by charge, dotted in to a differential line element dl. And I'm going to pull that 1 over Q term out. Which leaves me with 1 over Q multiplied by the integral of F dotted into dl. So what's F dotted into dl? You guys have Physics 201, right? Some of you guys are, mechanical and civil engineers. You should know this. It's force times distance. Work. That's the integral definition of work, multiplied by a factor of 1 over Q. So what that tells us is voltage is just the work required to move a charge from point A in a circuit to point B in a circuit. That's it. All right, I didn't really give myself enough room, so I'm going to move this bit down real quick. We're going to get the other definition. All right, so since charge is a conservative quantity, meaning it can't be created or destroyed, this line integral is a conservative line integral, meaning that if we went all the way around a closed path, so if we went from A back to A, our answer would need to be 0, okay? Because we have a conservative quantity, that means that our line integral is also path independent. okay? So it doesn't matter what route we take to go from A to B, it always gives us the exact same answer. So from really the fundamental definition of how conservative line integrals work, we can say that voltage is simply the difference in electric potential between 2 points in a circuit. That second definition is the one that we're going to utilize the most in this class. It's probably the easiest one to kind of understand as well. But that first definition is very important because it tells us that we can't have current effectively in our system without voltage somewhere, because the voltage is the push that causes current to flow. It's the energy transfer that moves electrons around in our system, okay? So we cannot have any current flowing in a system if we don't have a voltage to push it in a particular direction, all right? Fundamentally, we probably all know this because if you have an electronic device, you need batteries to make it do anything. Voltage is the quantity that batteries provide, right? So in order to turn the device on, in order to have any sort of energy transfer or anything like that, we need a voltage somewhere in our system to push that current around. And then the second definition is really the one that we're going to use in this class that just says voltage is the potential difference between 2 points in a circuit. So let's say that I have a generic circuit element A. And now we're going to talk about the different ways that voltage is represented in a circuit, okay? So the first is through using polarity, okay? So we have this two-terminal element, element A, and we are going to assign a positive polarity to one terminal and a negative polarity to the other, and we indicate these polarities with a plus and a minus sign, okay? So our voltage A, the voltage drop over element A, has both a magnitude and a polarity, okay? Where the positive polarity terminal is assumed to be at a higher electric potential than the negative polarity terminal, which is what the plus and minus bit means, okay? So if I say that VA is 3 volts, that means that this terminal here is at 3 volts higher of an electric potential than this guy down here. That's all it means. Okay. If I defined, the polarity with a negative polarity on top and the positive polarity on bottom, what should the magnitude of my voltage be? It'll be -3 now because it's of opposite polarity. So if we had that VA on the right-hand side of 3 volts, positive polarity on top, negative polarity on bottom, that is the exact same thing as -3 volts, positive polarity on bottom, -3 on top. So we're saying that the potential at the bottom terminal is -3 volts higher than the polarity on top, which is the same as +3 volts higher. All right, so this is one way that we represent voltage in circuits. It is the way that I prefer, but it is not the only way. So current, there's really the only way. You have a magnitude and a direction, okay? For voltage, we have this method, which is the one that we're going to use throughout this class. And then I'm going to talk about two more, just because I know that some of you are going to watch like YouTube videos and all that kind of crap to try to figure out what the hell it is I'm talking about. And you might watch a YouTube video from a person from a different country or something like that, and they have slightly different ways to represent voltages. So I just want to make sure that you understand how that relates to what we are doing, okay? So the second way that you can represent a voltage in a circuit, let's still use just this generic element, VA. I'm going to put a label on this terminal. Let's call this guy up at the top 1 and this guy 2. And so I could say that V12 is equal to 3 volts, okay? Where this is what's called a double subscript notation, because there are 2 subscripts. The first character in the subscript is the positive polarity terminal, and the second character in the subscript is the negative polarity terminal. So this is the exact same thing as us saying VA with positive polarity on top, negative polarity on bottom. So from that, if we flip the order of the subscripts, that is the exact same thing as flipping the polarity of the voltage. So in this case, that would be negative 3 volts. This methodology is fairly common. It's used here in the States as well in like 3-phase power systems and all that kind of good stuff. When you have a lot of nodes and you need to know how things, you know, what voltages are with respect to other points in the circuit and all that kind of stuff. A double subscript notation is probably a little bit cleaner to use than having plus and minus signs literally all over the damn place. So this guy does get used here in the States quite a bit. Not so much in this class, but again, some of you are going to try to supplement what I'm trying to teach you with YouTube videos and random free textbooks and all that kind of stuff. So it might be helpful to understand what's going on. The third method is the European method of denoting voltages, and it is the one that I care for the absolute least. I don't have anything against European people, but the way that they represent voltages drives me insane. And the reason is they represent the polarity portion with an arrow, which to me makes it super confusing because arrows are for currents. So if you see something like this, the head of the arrow is the positive polarity terminal. The tail of the arrow is the negative polarity terminal, which means this guy would be negative 3 volts. This will be the only time you ever see me use that hippy-dippy European voltage convention. I don't care for it. I think it's confusing because arrows, like I said, are for currents, but I just wanted to make you all aware of it. All right. So any questions on representing voltages in a circuit? All right, let's talk about voltage sources then. So the first one that we'll talk about is the one that you're probably the most familiar with from your Engineering 120 series. And that's this guy, where a voltage source is represented by 2 parallel lines, one of which is longer than the other. So in this case, the long line is the positive polarity terminal, and the short line is the negative polarity terminal. And this is the schematic symbol for battery. Battery is an example of an independent voltage source. Where that definition of independent that we came up with earlier still holds true. So an independent voltage source means the amount of voltage being provided by the battery in this case is fixed regardless of what it is connected to. That's true for an ideal battery. It's not remotely true for a real battery, but in this class, we're largely only going to deal with ideal quantities. Okay. Our next voltage source is this guy. This is a generic DC voltage source. It is also independent. And effectively, for the purposes of this class, it's just a slightly different way to draw a battery. That's my preferred method to represent DC voltages, or at least DC voltage sources, because there is explicitly a positive polarity terminal indicated by the plus sign and a negative polarity terminal indicated by the minus sign. So there's no opportunity for me to confuse it or anything like that. Also, two parallel lines to me means we have a capacitor. So this is just a representation that always means DC voltage source, no ambiguity, can't mean something else ever. This is always a DC voltage source. We have another representation. Plus and a minus sign with a squiggle in the middle. And then we'll have Vs of t. So this is an AC voltage source. It is also independent. Then we have this guy. And this guy, both of which are dependent voltage sources. The one on the left, our dependent voltage source on the left is a voltage controlled voltage source, and the guy on the right is a current controlled voltage source. And both of these guys are dependent. The units for K are volts per volt. And the units for R here are volts per amp. Again, they have the exact same symbol, and you tell if it's a voltage controlled voltage source or a current controlled voltage source by looking at whether or not it depends on a voltage or a current. So just to really hammer this home, because it can be confusing, that guy on the right there is dependent because it's a diamond. It's a voltage source because there's a plus and a minus sign in the middle of it. And it's current controlled because it depends on a current I or IX, okay? So anytime we see an arrow, it means we have a current source. Anytime we see a plus or a minus sign, it means we have a voltage source. I know I'm probably harping on this a lot, but you'd be surprised how many people kind of forget it and then make simple mistakes. All right, so that takes care of charge, current, and voltage. Anybody have any questions about those three quantities? We're in the home stretch here. I'm almost done talking. All right. So the next thing that I want to talk about is power and energy. Power is the rate per unit time at which electrical energy is transferred. Mathematically, E is equal I times V. The unit of power is the watt, which is exactly equal to 1 volt amp, or 1 joule per second. So our definition for power didn't change at all between engineering of 120 and now, so you can still remember the I've got the power thing or whatever that Dr. Corbett teaches. P is equal to I times V, always, always, always. Energy is the total amount of power transferred over a fixed period of time. So mathematically, that looks like W is the integral from T1 to T2 P of T dt, where the unit of energy is the joule. Okay. So our mathematical definitions are pretty straightforward. What I am about to introduce next is probably something that is going to take some time to click for an awful lot of you. I'm telling you this now, you will be tested on this next concept on every exam that I give you, because it's super critical that you understand what's going on here, okay? So what I'm about to talk about is called the passive sign convention. So let's say that I have a generic circuit element and I have a voltage drop VA over this element. Positive polarity on top, negative polarity on bottom. Let's say that I have a current flowing through element A. And it is flowing into the positive polarity terminal and out of the negative polarity terminal. This element is absorbing P is equal to IA times VA, and it is supplying P is equal to, negative IA times VA. Seems trivial. And it feels trivial to me because I'm a jackass with a PhD who's been doing this crap for 15 years. Okay, so I'm not trying to say it's not confusing for you guys because this is very likely the first time you've seen it. I have just kind of stopped understanding why it's not trivial because I've done it so many times. That being said, I'm absolutely happy to explain it over and over and over again throughout the class because it's necessary to understand some things. So effectively, what this guy says is when the current is flowing into the positive polarity terminal, the product of V and I is the absorbed power. Okay? It does not matter if V is a positive voltage or a negative voltage. It does not matter if I is a positive current or a negative current. When the current is flowing into the positive polarity terminal, the product of I and V gives you the absorbed power. Supplied power is nothing more than negative absorbed power. Okay? Now let's look at the alternative representation. Let's say that we have this exact same element A. We have the voltage VA like so, but we change the direction of the current so that now the current is flowing into the negative polarity terminal and out of the positive polarity terminal. This guy is absorbing E is equal to negative IA multiplied by VA. And it is supplying E is equal to positive IA times VA. And again, it does not matter whether the voltage or current is positive or negative. This is the rule. When current flows into the positive polarity terminal, I times V is the absorbed power. When current flows into the negative polarity terminal, I times V is the supplied power. Absorbed power is just negative supplied power and vice versa. I would legitimately get into the habit of writing these little rules on the top of your paper whenever you're working these first several homework sets and stuff like that, to just be able to refer back to it over and over and over again. Because you're going to be asked questions on your homework sets, on your exams, all that kind of good stuff, to calculate the absorbed power by so-and-so element, or calculate the power supplied by blah, blah, blah. And you're going to do everything mathematically right, but your answer is going to be wrong until you change the sign, and this is the reason. So understanding this is going to save you tons and tons of headache. I'm telling you this right now, as I mentioned a few minutes ago. I'm going to test you on this over and over and over again in this class. I am absolutely that jerk who is going to put the same numerical answer on your multiple choice test twice, once with a positive sign, once with a negative sign, and expect you to know which one is correct. You will get 0 credit if you choose the wrong one. So understanding this is fundamental to you not having crap exam grades. Are we very, very clear? Okay. If you look at any of the practice exams and all that kind of stuff, which I've already uploaded, this crap shows up 2 to 3 times on each test. And with questions worth 4 points apiece, that's the understanding it versus not understanding it is literally a letter grade, okay? So I'm happy to re-explain it if it trips you up and all that kind of good stuff. I'm also happy to shut the heck up about it and let you guys work on some things because I've talked for an hour and 10 minutes at this point. So anybody have any question regarding the passive sign convention, power, energy, or anything like that? All right, I'm done yammering for today.